Hello guys. In this lecture we want to introduce another class of machines. Let's see what's the objective of this lecture. So far we introduced two classes of machines, DFAs and NFAs that are equivalent and PDAs. And also we learned their limitation. Now we want to introduce a new class of automata, and definitely we will expect that this new class should be more powerful than them. We have a roadmap for to introduce a new class of machines, and we will be following the same roadmap. So the first question is, why do we need a new class? This is our last conclusion. We learned DFAs and NFAs that recognize a small portion of the formal languages that we call them regular languages. Also, we learned that PDAs will accept a bigger portion of the languages that we call them context-free, but we still don't know what's the meaning of the context-free. Then we learned that there are some languages like this, A to the N, B to the N, C to the N, or WW. These languages cannot be recognized by PDAs. So it is reasonable that we are looking for some kind of machine that at least it can recognize some of the non-regular languages that can be accepted by PDAs. So what was missing in PDAs? We used a memory that was a stack, right? We used a stack for storing and counting, but what is the problem with the stack? It is not flexible for storing and retrieving. Why it is not flexible? Because we lose some data when we access the older data. What does it mean? Let's say this is a stack, yeah? And let's say we have some information here and the top of the stack is here, right? And if we want to access the information here, then we need to pop all of these stuff and reaches here, right? It means that when we pop all of these stuff, it means that we are losing them. That's why we say, hey, stack is not so flexible, right? Okay, so now what? Now we are looking for more flexible memory. Like what? Like something that we can read and write, and we can, control the head or cursor to move it around and get any information that we want. That's the goal that we are looking for. Second question is, what's the name of this new class? This new class was proposed by Alan Turing in 1936. That's why we call it Turing machine. Okay, both deterministic and non-deterministic Turing machines can be defined. For the deterministic one, we call it a standard Turing machine. Sometimes for simplicity and so for convenience, we can eliminate or we can skip the standard. We just say Turing machine. So when I say Turing machine, we really mean that deterministic Turing machine or a standard Turing machine. And if we want to mention non-deterministic Turing machine, explicitly we use this as the prefix, non-deterministic Turing machine or NTM. Okay. Before going further, let me explain very briefly who was Alan Turing. Alan Matson Turing, 1912 until 1954. Just look at the age. He was only 42 years old when he died. So he was born in Britain, and he was mathematician, logician, cryptanalyst, theoretical biologist, and he is known as the father of the theory of computation, discourse, and artificial intelligence. So this guy is the initiator of computer science, and he's one of the most effective, pioneering computer scientists. I put the longer version of who is Alan Turing in the Appendix A for your reference. The third step is the building blocks of the Turing machines. So Turing machine has two main parts or two main blocks: input-output tape and the control unit. Let's see each block in detail. The input-output tape looks like this. It is unbounded from both sides, and it is divided into the cells, and each cell can hold one symbol. And the input string is written somewhere on the tape when you start your machine. And the rest of the tape will be filled with the blanks that looks like this, an empty square like this. And there is a read-write cursor or read-write head that after starting your machine, it always points to the leftmost symbol of the input string. Okay, so its job is to read a symbol, to write a symbol, and move left or right based on your algorithm. So as you see, the tape of the Turing machine is so simple. The only thing that we added here is the capability of writing and also moving from left to right. So far, all of the tapes, we couldn't move the tape to the left. Always we needed to move it to right. And it was automatically done by the machine. But for the Turing machine, we can move it by the code. How the control unit is structured? The control unit is, as usual, is a transition graph, and it looks like pretty much to the PDAs as you see. Yeah. The only difference is the edges that it looks a little bit different. If you pay attention precisely, you will see that we have A and then semicolon X comma R, but in the PDAs we had a something like this, a comma b and then semicolon and something else, let's say xy. So the semicolon is replaced here, the semicolon is relocated here instead of here, and we will explain that what's the meaning of each part. Each label has three parts, and they are delimited by a semicolon and a comma. You see here. The first symbol is whatever should be read from the input-output tape. The second symbol is whatever that should be written wherever the head is pointing. And the third one is the move direction. R is equivalent to right, and if you put L there, it means that we would like to move the head or cursor to the left. So R and L, both of them are reserved symbols. They are called move symbols. Now let's see how Turing machine works. So we would need to answer four questions. What is the starting configuration? What would happen during a time frame when machine halts? And how they accept or reject a string. The starting configuration looks like this. So as usual, the clock starts with the 0 and the control unit starts from the initial state. And the input-output tape looks like this. The string will be written somewhere. We don't mind really where because all of them are the same. And the rest of the tape will be filled with the blanks, and the head will point to the leftmost symbol of the string. So this is the starting configuration. Second question, what happens during a time frame? As you know, during the time frame, many tasks will happen, and the combination of all of those tasks is called transition. But before we can explain that precisely, let me visualize those tasks through some examples. Then we will summarize the whole things in one slide. In these examples, I will show you a partial transition graph, an input-output tape and its content, a clock, and then we assume that we are in time frame n, and the question is what would be the configuration of the machine at time frame n plus 1. Example 1. So this is the configuration, and this is our transition. It is saying that if the input is B, change it to H. Change it to H, it means that write H wherever the cursor is pointing. So cursor is pointing to here, and this is a checking that it is B. Yes, it is B. Then write H. Instead of B, in the next slide, we will see H here. And then this guy is saying that move to the right. So in the next slide, we expect to see something like this. That's how it works. Okay, so with this simple example, we can now respond to this question. What happens during a time frame? A symbol at which the cursor is pointing is red, and that symbol actually is the condition for the transition. A symbol will be written into the same cell, and the cursor moves one cell to the left or right based on the algorithm, and the control unit makes its move based on a logic of transition that we know that it is an if-then statement, right? Okay, before going further, let's see what is that if-then statement in detail. So here is the if-then statement. If the input is X, so this is the condition for transition, and it is really X in this particular example, then the operations part comes here. So replace X with Y, because this is the Y, and move the cursor to the left because of this, could be right if it was R, and transit from Qi to Qj. So it looks like simpler than the PDAs because we just have one condition for transition, and that's the input symbol, nothing else. But we have the ability to write something, and we have the ability to move the cursor left or right. This is a huge difference, actually. As you will see, these two things will make a huge difference to the power of this machine. How does the machine look like after this transition? Very easy. So this will be replaced by Y, and since it is L, then machine moves the cursor to the left like this. Okay, the natural question raises here, what if the input is not X? Yeah, I'm sure that you can guess that what would be the behavior of the machine, but yeah, let's keep it here and we will get back to this question later. As usual, we can have multiple labels, something like this. And we know that between these two, there exists an or. Whichever condition is satisfied, machine moves from Qi to Qj and does the appropriate operations. Another example. So if the input is C, change it to M and move to the left. The input is C, it will be changed to M, and cursor move to the left. Another example. If the input is B, change it to F and move to the left, but the input is not B, right? So here, the condition for transition is not satisfied. The best behavior for this is halting, right? So the machine halts. Halts where? In the Q12 in this example. All right. Based on this explanation about the how machine works, now we can finish our when Turing machines halt. The transition condition is input symbol. When it is not satisfied, then machine halts. And here is the logical representation of halting. So machine halts when it has zero transition. Now the question is how Turing machine accept or reject strings. Recall that our standard logical representation was something like that. H and C and F, then accept. What does it mean? Halting, consuming, and being in final state is equivalent to accepting a string. And for the rejection, we just need to negate both sides and apply the De Morgan's law. And we are so familiar with this. But the point is, for the Turing machines, accepting and rejecting needs really more attention. We need to be more precise about this, and we will need more knowledge. So let's get more knowledge by analyzing some Turing machines, then we will get back to this question. Turing machines in action. Let's start with analyzing some Turing machines. In this example, we want to trace this Turing machine against this input string. Okay, as we explained before, the input string will be written somewhere on the tape, and the rest of the tape will be filled with blank symbols. Now let's look at this machine and see what we got here. We have two labels here. One of them is saying if the input is B, then don't change it and go to the left. This one is saying that if the input is A, change it to B and go to the right. All right, the input is A. So in the next slide, we would expect that this will be changed to B and the movement is to the right. So the cursor will go here. Let's see. How about the next one? Again, this condition is satisfied. So machine does the same thing and move to the right. Now what? Now this guy is no longer satisfied, but this guy will be satisfied. It is B and change it to B. Let's say it doesn't change it and then go to the left. And the same thing. And now what? Now the input is blank and this guy will be satisfied. So it doesn't change the blank and it goes to the right to here. Now what? Now machine is in Q1 and there is no more transition. So machine has to stop. Based on our definition for the halting, the machine has no transition, right? Okay, so it was in a accepting state and the last symbol, which is A, was not touched, was not reached. And here is the original string A, and this A never reached. I mean the cursor never reached to this symbol. So what problem we have here? We got this problem that if someone asks us, hey, was the string accepted? Then based on our criteria, which is this, halting, consuming, and being in final state, then we have a problem with the consuming. So based on these criteria, we would say no, because all symbols were not consumed. But wait a minute. Let me make some observations here. So the first observation, the original string is changed. What does it mean? It was AABA, now we have BBBA. So the original string is changed. And the second observation, in some cases, some symbols were visited several times, in this example twice. So it was AAB, and this guy was visited. This guy was visited twice. This guy was visited twice, but this guy was not visited at all. So this is the second observation. This makes a little bit the concept of consuming all symbols difficult, right? It looks like for Turing machines, consuming all symbols is meaningless. Why is that? Because we have the power to move left and right, and we have the power to change the original string, right? So here is our conclusion now. It is designer's job to keep track of the symbols that are consumed. So we need to make sure that we design the machine in such a way that all symbols are consumed, and it's not something that even JFlap can help you. JFlap doesn't sense this consuming at all, right? It does not give you any signal, hey, all of the symbols are consumed, or it does not keep track of the what symbols are changed or what are not. So everything is your responsibility as the designer. And all of these is the consequence of having power to move the cursor left or right. And probably it reminds you the Spider-Man quote that with great power comes great responsibility. Now you have the power to move the cursor left or right or change the strings, and this great power will bring great responsibility. You need to keep track everything by yourself. Let me ask this question here. What does this Turing machine really do? You may pause the video and try to think about that and come up with an answer. The original string was A, and when machine finished its job, it becomes B. So it means that all of these A's change to B's. So in other words, if we put a string like A to the N, let's say BA, and after this A, it can be anything, right? In this string, yeah, we didn't care about the rest of that, but it can be anything after the A. So this pattern was changed to B to the N, BAW. So this is the first thing that this Turing machine did for us. Another thing that it did was moving the cursor from here to the beginning of the string. So this Turing machine did two things, right? Another example, trace the following Turing machine against AB. So if the input is A, don't change it, go to the right. So the input is really A, don't change it and go to the right. Machine transit to Q1. Now what? If the input is B, don't change it, go to the left. All right. Again, if it is A, don't change it, go to the right. What's happening? Go to the left. Don't change it. So when does it halt really? Never. What is this phenomena? Yeah, the machine never halts. And it means that in some cases, Turing machine can fall into an infinite loop. And this never happened for any previous deterministic machines, right? Was the string accepted based on our standard criteria? Halting never happens. So, no. Okay, this is another consequence of having the power to move to the left or right. Now let me summarize our observations so far. So we noticed that we have two new abilities. We can move the cursor left and right, and also we can write any symbol anywhere. So what are the consequences now? We may revisit all or part of the symbols of the input string several times, and some of them can be untouched. What else? We can change the original string, and also Turing machine may fall into an infinite loop. All of these are the consequences of these two new abilities that we have. Okay, now let me define officially when a machine will accept a string. So we will be using our standard way of accepting. So it means that we would need all of these three conditions: halting, consuming, and being in final state. But I would like to emphasize one more time that for the Turing machine, consuming is done by you guys as the developer, and JFlab won't help you. All right, it's your responsibility to make sure that all of the symbols are consumed. How about the rejection? Yeah, just the negation of this accepting, and you guys are so familiar with this. All right, this lecture has accompanied with another JFlap tutorial for working with Turing machines that need to be watched. Okay, I'm gonna stop here. See you guys in the next lecture.